This question looks at properties of ion compounds and iron ions in different oxidation states. Part A. Fe2 plus and Fe3 plus are the most common ions of iron. Part 1. Write the electron configuration in terms of subshells for the Fe2 plus ion. If we were to write the electron configuration of ion, that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. The 4s electrons are added first and lost first, so when forming a 2 plus charge we would lose our 4s electrons. That would make the electron configuration of Fe2 plus 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. To get the mark for this question, you must have the correct electron configuration. Part 2. How many orbitals contain an unpaired electron in an ion of Fe2 plus? The unpaired electrons would be in the d subshell. If we were to write the d subshell, we would draw it as 5 squares because we could have a maximum of 10 electrons, and we would singularly fill each square once with 1 electron spinning up, but then we have 6 electrons because of 3d6, so we're going to have an electron spin down. That means we've got 4 orbitals with an unpaired electron in Fe2 plus. To get the mark for this question, you must write 4 on the answer line provided. Part B. FeH2O6 3 plus ions take part in ligand substitution reactions. An excess of aqueous potassium cyanide, KCN aqueous, is added to an aqueous solution containing FeH2O6 3 plus ions. A ligand substitution reaction takes place forming a complex ion that has a molar mass of 211.8 grams per mole. Write an equation for this ligand substitution reaction. This is a ligand substitution reaction, so that means that the H2O ligands will be substituted with cyanide ligands. So if we were to write this equation, we would have FeH2O6 3 plus 6Cn minus goes to FeCN6 3 minus plus 6H2O. So how we've got to this equation? Well, we've used the information in the question. So we're told that the complex has a molar mass of 211.8. So if we were to work this out, this gives us how many cyanide ligands we're going to have. So we do 211.8 minus 55.8. That's the molar mass of iron, and that gives us 156. And then we do 156 divided by 12 plus 14. So that's the molar mass of cyanide, and that equals 6. So that shows us that we're going to have 6 cyanide ligands. And then we need to look at the charge to confirm this is the correct charge. So iron in this question has a 3 plus charge. So with water, which is a neutral ligand, it would have a 3 plus overall charge for its complex. But for cyanide, which has a negative charge, if we've got iron 3 plus and cyanide 6 minus, because there are 6 of them, each with a minus charge, we're going to have plus 3 minus 6, which gives an overall charge of minus 3, which is what we can see here, or 3 minus. To get the marks for this question, you get a mark for having FeCN6 3 minus as your product, or your complex ion. And then you get your second mark for having the rest of the equation correct. Part C. The complex ion FeH2O6 3 plus behaves as a weak Bronsted-Lowry acid in aqueous solution. The equation below represents the dissociation of aqueous FeH2O6 3+ ions together with the Ka value. Part 1. Write the expression for the acid dissociation constant, Ka, for FeH2O6 3+. Looking at the forward reaction, we're going to have the products at the top. So we will have FeH2O5, OH, square brackets 2+, and then square brackets H+ on our top as our numerator, and we will divide by our reagents or reactants, FeH2O6 3+. To get the mark for this question, you must have the correct expression for Ka written. Part 2. Calculate the pH of a 0.1 mole per decimeter cube solution of FeH2O6 3+ to 2 decimal places. For this question, we're going to make the assumption that the concentration of H+ and the concentration of FeH2O5OH is the same. And that means we can write Ka equals H+ squared divided by FeH2O6 3+. So, when given the values in the question, we can rearrange to find the concentration of H+. The concentration of H+ would be the square root of 6 times 10 to the negative 3 multiplied by 0.1. That equals 0.0245 moles per decimeter cubed. Now we're going to use the equation of pH equals negative log 10 H+, and because we worked out our H+ concentration, we can work out the pH using minus log 10 0.0245. That gives us a pH of 1.61, which we then write on the answer line provided. To get the 2 marks for this question, you get your first mark for correctly working out the concentration of H+, and your second mark for correctly working out the pH and writing your answer to 2 decimal places. Part D. Fe2O3 can be oxidized by Cl O- ions under alkaline conditions in a redox reaction. Unbalanced half equations for this reaction are shown below. Balance the half equations and construct an overall equation for the reaction. Balancing our first half equation, we need 2 OH- ions because we have 2 hydrogens on the left, which we don't have on the right. Then balancing the charges, we need 2 electrons. For our second half equation, we need 2 FeO4 minuses because we have 2 Fe's on the left and we don't have that on the right, but now we do. Then we need to balance the oxygens. We're going to have 10 OH- ions, and that's going to produce 5 waters. Finally, balancing the charges, we need 6 electrons. When writing our overall equation, we need to multiply our first half equation by 3. Then that's going to make our overall equation Fe2O3 plus 3ClO- plus 4OH-, and that's going to produce 2 FeO4 plus 3Cl- plus 2 H2O. To get the 3 marks for this question, you get a mark for each half equation that's correct and a mark for the correct overall equation.